The meter room at the Consolidated Iron Works sits in near darkness at 5:47 in the morning. Through the single window facing east, the sky is beginning to pale. The iron casing of the gas meter stands motionless against the brick wall, its brass fittings catching the first weak light. Inside, the mechanical heart of the device, gear trains, a leather diaphragm, ratchet wheels, waits in stillness. The factory will not light its forges for another hour. The pipe network beyond the meter room stretches silent through 3 buildings: the casting hall, the finishing shop, the boiler house. In this moment before dawn, everything is cold. The brick walls have surrendered the previous day's heat to the October night. The iron pipes, buried in trenches between buildings, have equilibrated with the earth around them. At 5:51, something happens. The needle on the meter face, a painted steel indicator resting at yesterday's final reading, begins to move. Not forward, as it does when gas flows toward the factory. Backward. The motion is slow enough that a man standing directly before the dial might doubt what he's seeing. But it is unmistakable. The needle travels counterclockwise across the numbered face, reversing the cumulative count by small, precise increments. There is no hiss of escaping gas, no smell of leakage. The building is locked. The valves downstream remain closed. Yet the meter records, with mechanical certainty, that gas is flowing in the wrong direction. By 6:15, as the first workers arrive and daylight fills the meter room, the needle has crept backward through nearly 8 cubic feet of registered volume. Then, gradually, it stops. For a moment, it holds position. Then it begins moving forward again, as meters are supposed to do, as the factory wakes and begins drawing fuel. The night watchman, making his final rounds before shift change, notices nothing. The day supervisor, arriving at 6:30 to check yesterday's consumption figures, sees only the current reading. But when the plant accountant compares this morning's number against last night's logbook entry, he finds an impossibility. The meter shows less gas consumed than it did 8 hours earlier. He assumes a transcription error. He checks the log again. The figures are clear. He goes to the meter room himself, inspects the mechanism, finds nothing obviously wrong. He makes a note in his ledger and moves on. The next morning, it happens again. For 3 consecutive days, the morning meter reading is lower than the previous evening's record. Not by much, between 6 and 10 cubic feet each time. But the discrepancy is consistent and measurable. On the 4th morning, the accountant asks the night watchman if anyone has accessed the meter room overnight. No one has. The room remains locked from evening until dawn. The watchman carries the only key. On the 5th morning, the accountant arrives early. He stands in the meter room at 5:30, lantern in hand, and watches. The factory is silent around him. Through the window, the sky lightens from black to deep blue. At 5:48, he sees the needle begin its backward journey. He moves closer, examining the mechanism for any sign of tampering. The casing is intact. The seal is unbroken. The gears inside turn smoothly, honestly, recording whatever motion the diaphragm assembly communicates to them. Watches until 6:20, when the reversal stops. He records the exact amount, 7.3 cubic feet backward. Then he waits through the morning as the meter returns to normal operation, counting forward as workers light furnaces and gas flows into the plant. That afternoon, he brings the observation to the plant superintendent. The superintendent's first theory is theft. Someone has found a way to reverse the meter mechanically to conceal their unauthorized use of gas. But the mechanism shows no signs of interference. The backwards flow always occurs when the factory is locked and empty. And crucially, if someone were stealing gas, the meter would show less consumption than actual. But the reversal is too small and too predictable to be deliberate fraud. The superintendent's second theory is instrument failure. The meter, a rotary displacement type manufactured by the American Meter Company, is 7 years old. Perhaps the gears have worn unevenly. Perhaps the diaphragm has developed a slow leak that only manifests under certain conditions. He orders the meter removed and sent back to the manufacturer for inspection. The replacement meter, installed 3 days later, does exactly the same thing. Every morning, just after sunrise, the needle creeps backward. The amount varies slightly, some mornings 5 cubic feet, others nearly 10. But the direction is always the same. and the timing is always within the same narrow window, from shortly before 6 o'clock until shortly after. By November, the pattern has continued for 6 weeks. The accounting department, responsible for reconciling gas bills against meter readings, can no longer ignore the discrepancy. Each morning's reversal erases a measurable quantity of recorded consumption. Over a month, this amounts to more than 200 cubic feet, gas the factory has paid for, but which the meter insists was never used. The gas company, when presented with the complaint, sends an inspector. He examines the meter, the piping, the pressure regulator upstream of the meter. Everything is in order. He observes the meter during daylight hours and sees nothing unusual. He suggests that the plant's record keeping is at fault. The plant superintendent, a man named Howard Breslin, takes this as an accusation of incompetence. He arranges for a demonstration. On a cold morning in mid-November, the gas company inspector, the meter manufacturer's regional representative, and Breslin himself stand in the meter room before dawn. At 5:46, as the sky begins to lighten, the needle starts moving backward. The inspector from the gas company leans close, watching the dial. "How long does this continue?" 30 to 40 minutes, Breslin says. "Always in the same window after sunrise." The manufacturer's representative checks the seals, examines the gear train through the inspection port, listens to the mechanism. "The meter is functioning correctly," he says. "If the needle moves backward, gas is flowing backward. That's what the instrument is telling you." "That's impossible," the gas company inspector says. "Gas flows from the main line toward the customer. It can't flow the other way. There's nowhere for it to go." The representative shrugs. "I'm telling you what the meter is doing." Whether the reading makes sense is a different question. They stand in silence, watching the needle crawl across the dial. By 6:30, it has reversed through 8 cubic feet and stopped. Shortly afterward, it resumes normal forward motion. The gas company inspector proposes a test. If gas is truly flowing backward, they should be able to detect it at the supply main. He arranges for pressure measurements to be taken at the street connection during the next morning's reversal. The readings show no anomaly. The system pressure remains steady. Breslin proposes a different test. He orders the main shut-off valve, located between the street connection and the meter, closed overnight. If gas is flowing backward from inside the plant, closing the valve should prevent the reversal by blocking the path out. On the night of November 19th, after the factory shuts down, the valve is closed and locked. The next morning, the meter needle moves backward any. A gas meter is, fundamentally, a device for measuring volumetric flow. The specific type installed at Consolidated Iron Works is a rotary positive displacement meter. Inside its iron casing, gas enters through an inlet port and fills a chamber bounded by a flexible leather diaphragm. As the diaphragm expands, it pushes a mechanical linkage that turns a gear train. The gears, through a series of reductions, drive the indicator needle on the dial face. Each complete cycle of the diaphragm corresponds to a fixed volume of gas, in this case, 1 cubic foot. The mechanism is designed to be directional. Gas pressure pushes the diaphragm in one direction only, from inlet to outlet. The gear train includes a ratchet mechanism that should prevent backward motion. Even if pressure somehow equalized across the meter, the ratchet should lock the gears and hold the needle in place. But the meter at Consolidated is moving backward. This means one of three things must be true. Either the ratchet is failing, or pressure is reversing across the meter strongly enough to overcome the ratchet, or gas is genuinely flowing in reverse, and the mechanism is recording it honestly. The manufacturer's representative, examining the meter after it was removed, finds the ratchet mechanism intact. The pawl engages cleanly. There is no wear that would allow backward slippage under normal conditions. However, he notes something subtle. The ratchet is designed to hold against accidental reversal, not against sustained pressure. If gas flow actually reversed, with sufficient pressure differential, the ratchet would yield. It would click backward, tooth by tooth, allowing the gears to turn in the opposite direction. This raises the essential question. How could gas flow backward through a distribution system designed specifically to prevent such a thing? The pressure regulator upstream of the meter is a diaphragm type, designed to maintain constant downstream pressure regardless of variations in the supply main. When demand increases, when the factory lights more burners, the regulator opens wider to maintain pressure. When demand drops, it closes. At night, with no consumption, the regulator should be nearly closed, maintaining just enough pressure to keep the downstream pipes filled. But pressure regulators of this era are not perfect. They exhibit hysteresis. Their response to increasing pressure differs from their response to decreasing pressure. A regulator closing under falling demand may not seal completely. It may allow a slight trickle of gas to continue flowing, maintaining pressure on the downstream side. Now consider the pipe network itself. From the meter, pipes run underground to 3 separate buildings, totaling more than 800 feet of 2-inch iron pipe. This represents a substantial volume of contained gas, approximately 12 cubic feet when pressurized. This gas is not static. It responds to temperature changes, to pressure variations, to the slow equalization that occurs in any fluid system at rest. In December, Breslin begins keeping detailed environmental logs alongside the meter readings. He records outdoor temperature, indoor temperature in the meter room, barometric pressure, wind direction, and the exact time of sunrise. He is looking for correlation, for any pattern that might explain why the reversal happens when it does. The data reveals something immediate. The reversal only occurs on clear, cold nights. When the temperature drops below freezing overnight and the morning dawns cloudless, the backward flow is most pronounced. On overcast nights, or when temperatures remain moderate, the reversal is smaller or absent entirely. This observation points toward thermal effects. Gas, like any substance, changes volume with temperature. When gas cools, it contracts. When it warms, it expands. The question is where this expansion and contraction is occurring and how it might drive flow in the wrong direction. Breslin arranges for temperature measurements to be taken at multiple points: at the meter, in the casting hall, in the buried pipe trenches. The results show significant thermal lag between different parts of the system. The casting hall, heated by residual warmth from the previous day's furnaces, cools slowly through the night. The pipes, buried 18 inches underground, cool even more slowly, insulated by earth. But the meter room itself, a small brick structure with a single window, cools rapidly once the sun sets. By dawn, the temperature differential is substantial. The gas in the meter, exposed to the cold morning air in the unheated meter room, may be 10 or 15 degrees colder than the gas still sitting in the underground pipes leading to the factory buildings. Cold gas is denser than warm gas. At equal pressure, cold gas occupies less volume. Breslin begins to form a hypothesis. Overnight, as the factory sits idle, the gas in the meter room cools rapidly. It contracts. This creates a slight pressure differential. The gas in the warmer, buried pipes is at fractionally higher pressure than the gas in the cold meter room. The pressure regulator, closed but not perfectly sealed, cannot equalize this difference rapidly. For a brief window each morning, as the temperature differential reaches its maximum just before sunrise, gas flows backward, from the warmer pipes toward the cooler meter. To test this, Breslin arranges for the meter room to be heated overnight. A small coal stove is installed and kept burning through the night, maintaining the room temperature above 50 degrees. For 3 consecutive nights, the room stays warm. On all 3 mornings, the meter needle does not move backward. The gas company inspector, reviewing Breslin's notes, remains skeptical. Even if there's a temperature difference, the pressure regulator should prevent reverse flow. That's what it's designed to do. Unless, Breslin says, the regulator itself is part of the problem. In January of 1893, the gas company agrees to a comprehensive investigation. They send not an inspector, but an engineer, a man named Gerald Tompkins, who has spent 15 years studying pressure regulation and flow dynamics in urban gas systems. Tompkins arrives with instruments, manometers for precise pressure measurement, thermocouples for temperature logging, and a deep skepticism about simple explanations. He begins by mapping the entire pipe network. From the street main, gas flows through a reducing valve into a 4-inch supply line. This line runs 30 feet to the pressure regulator, which reduces the pressure from street main levels, typically around 8 inches of water column, down to 4 inches, the operating pressure for the factory equipment. From the regulator, gas passes through the meter and then splits into 3 branch lines running to the different buildings. Tompkins measures the volume of gas contained in this system, approximately 18 cubic feet total. He notes that the buried pipes are cast iron, heavy-walled, installed in trenches that are wet from groundwater infiltration. Water has excellent thermal mass. It will keep the pipes at a relatively stable temperature, even as air temperature fluctuates. Next, he examines the pressure regulator in detail. It is a spring-loaded diaphragm type, manufactured by the Fisher-Governor Company. The diaphragm responds to downstream pressure, opening or closing the valve to maintain setpoint. Tompkins tests the regulator's response under various conditions and discovers something critical. The regulator exhibits significant hysteresis. When pressure is falling, as it does overnight when consumption stops, the regulator closes slowly and does not seal completely. A small clearance remains, allowing gas to continue trickling through at a rate of roughly 1 cubic foot per hour. This trickle, Tompkins realizes, is essential to understanding the reversal. Overnight, the regulator maintains a slow feed of gas into the downstream system. This gas gradually replaces volume lost to leakage and slow consumption by pilot lights. But it also means that the downstream system never fully equilibrates. Pressure remains slightly elevated throughout the network, sustained by the regulator's slow feed. Now consider what happens as temperature drops. The gas in the meter room, exposed to cold air, contracts rapidly. Its volume decreases. If the gas were free to move, this contraction would pull gas from the downstream pipes into the meter, equalizing the volume. But the meter itself resists this flow. Its diaphragm mechanism creates resistance, and the ratchet mechanism opposes backward motion. For several hours, the system exists in a state of tension. Cold gas in the meter, warmer gas in the pipes, and insufficient pressure differential to overcome the meter's mechanical resistance. Then sunrise arrives. The first light warms the meter room, but slowly. The thermal mass of the building delays the temperature rise. For 30 to 40 minutes, a specific condition exists. The meter room is at its coldest, the buried pipes are still relatively warm, and the pressure regulator has allowed enough gas into the system overnight to create a measurable pressure difference. The gas in the warm pipes, at slightly higher pressure, begins to push backward through the meter. The ratchet mechanism, designed to prevent accidental reversal, yields under sustained pressure. It clicks backward, tooth by tooth. The gear train turns in reverse. The needle moves counterclockwise. The meter honestly records gas flowing from the factory back toward the street main, not because anyone is stealing gas, but because the thermal and mechanical characteristics of the system briefly allow it. The phenomenon at Consolidated Iron Works results from the convergence of 4 separate factors, none of which would cause reverse flow independently, but which together create the observed effect. First, thermal contraction of gas in the meter room. The meter is housed in a small, poorly insulated structure that cools rapidly on clear nights. By dawn, the gas inside the meter is 10 to 15 degrees colder than the gas in the buried pipes. Cold gas is denser. At constant pressure, it occupies less volume. This contraction creates a pressure imbalance, with the meter chamber at slightly lower pressure than the downstream pipe network. Second, pressure maintenance by the regulator. The Fisher-Governor regulator, like most spring-loaded designs of the era, does not seal perfectly when closed under falling demand. It maintains a slow trickle flow, approximately 1 cubic foot per hour, throughout the night. This keeps the downstream system pressurized at close to operating pressure, even with no consumption. Without this trickle, the pressure would decay slowly through minor leaks, and no reversal would occur. Third, thermal lag in the buried pipe network. The cast iron pipes are installed in wet soil, which has high thermal mass. They cool far more slowly than the exposed meter mechanism. This creates a temperature gradient, cold meter, warm pipes. The pressure of gas is temperature dependent. Warmer gas exerts higher pressure than cooler gas at the same density. The result is a pressure differential of several hundredths of an inch of water column, tiny in absolute terms, but sufficient under the right conditions. Fourth, mechanical characteristics of the meter itself. The rotary displacement meter uses a ratchet mechanism to prevent backward motion under normal conditions. But this ratchet is not designed to withstand sustained reverse pressure. When the pressure differential reaches a critical threshold, typically around 0.03 inches of water column, the ratchet begins to yield. Each click backward represents one tooth of engagement slipping. The gear train turns in reverse. The mechanism, operating exactly as designed, records the backward flow. The timing is critical. The reversal occurs only in a narrow window just after sunrise because that is when the thermal gradient is steepest. Earlier in the night, temperatures are still equalizing. Later in the morning, the meter room begins to warm, eliminating the temperature differential. Only during that brief period, typically 30 to 40 minutes, do all four factors align. Tompkins documents his findings in a technical report submitted to the gas company in February of 1893. He notes that the reversal is not a defect. It is a predictable consequence of the system's physical characteristics operating within the limitations of contemporary pressure regulation and metering technology. The meter is functioning correctly. The regulator is functioning correctly. The pipe network is installed correctly. Yet the system, as a whole, permits a behavior that none of its designers anticipated. The solution, Tompkins writes, is straightforward. Insulate the meter room to prevent rapid overnight cooling, or install a non-return valve immediately downstream of the meter to mechanically prevent reverse flow regardless of pressure conditions. Consolidated Ironworks chooses the simpler option. They insulate the meter room with sawdust packed between interior and exterior walls, and they install a simple flap valve in the outlet pipe. The valve allows forward flow with negligible resistance, but closes immediately if flow attempts to reverse. After the modifications, the backward creep stops. The meter reads forward only, as expected. The accounting discrepancies cease. But for Breslin, and for Tompkins, the episode reveals something larger about industrial measurement in the late 19th century. Instruments of this era are precise enough to detect behaviors that engineers do not yet fully understand. A gas meter records flow, but it does not know whether that flow is intended or expected. It simply measures what happens. And what happens, in complex systems operating near the limits of contemporary knowledge, is often surprising. The meter that ran backward was not broken. It was honest. It revealed that gas networks, like all thermodynamic systems, are more dynamic than they appear. Pipes are not passive conduits. Regulators are not perfect valves. Temperature is not uniform. And measurement, when sufficiently precise, exposes the complexity that simplicity conceals. Consolidated Ironworks continued operating for another 42 years. The gas meter, insulated and fitted with a check valve, never reversed again. But the episode was documented, discussed, and quietly referenced in engineering literature for decades afterward. It became a cautionary example, not of equipment failure, but of the gap between design assumptions and physical reality. The industrial age produced countless instruments capable of detecting phenomena that theory had not yet predicted. The meter at Consolidated was simply one of many that revealed, through meticulous honesty, behaviors the world was not yet prepared to explain.